Rational Approximation by Lloyd N. Trefethen. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading this article published in 2025 in the notices of the AMFs. Rational approximation is an old subject, but it has gone through a transformation in recent years with the appearance of a new algorithm that makes computing rational approximations easy. Indeed, many problems can now be solved to good accuracy in milliseconds on a laptop. This is the AAA algorithm, whose name derives from adaptive Antulus Anderson. Curiously, the computation of polynomial approximations on domains other than intervals and disks, which is in principle a much easier problem, but still becomes numerically intractable if a good basis is not available, has also been transformed recently by the introduction of the so-called Vandermonde with Arnoldi algorithm. The aim of this short story is not to describe how these algorithms, which has been done elsewhere, but to show how beautifully they can reveal the power of rational functions and the mathematics of rational approximation. With the help of 6 figures, all in the same format, we will illustrate what is sometimes called the Walsh-Gonchar theory of this subject. Details and references are found in various papers. The setting is a function f defined on a compact simply connected set k in the complex plane, and double bars are used for the infinity norm over k. Simple connectivity doesn't matter for the algorithm, but it makes this exposition simpler. We're interested in best or near best approximations to f by rational functions r of degree n, i.e. r equals p over q with polynomials p and q of degree n, and for comparison by polynomials of degree n. The minimax errors can be written error n equals infimum over all p of the infinity norm of f minus p, error nn equals infimum over all r of the infinity norm of f minus r. I suppose p must be ranging over polynomials here, and r over actual numbers? No, p is ranging over polynomials, r is ranging over ratios of polynomials. Figure 1, an entire function with f of z equals exponential function of z. First, consider the case where f is entire. Here it is known that both the error sub n and error sub n are guaranteed to decrease super exponentially as n goes to infinity, i.e. both are big O of c to the minus n for any c bigger than 1. Figure 1 illustrates this for approximation of f of z equals e to the z on the unit disk. On the left, we see convergence curves for AAA rational and Vandermonde with Arnoldi polynomial approximation, curving downward on this log scale. On the right, we see a portion of the complex plane with information about the final rational r approximation to accuracy 10 to the minus 12 of degree n equals 6 in this case. The red dots mark the poles pi k of r, 1 less than or equal to k less than or equal to n. The yellow dots mark a set of interpolation points zk with f of zk equals r of zk, 0 less than or equal to k less than or equal to n, that are selected by AAA in the course of its computation. Let's look at the figure again, the red dots, the yellow dots. The yellow dots are the interpolation points. The red dots are the poles. The AAA algorithm is a greedy iteration based on a barycentric representation of r with coefficients determined by a least squares minimization. There may be other data points besides the zk where r also interpolates the data, but the plots just mark these n plus 1 support points explicitly selected step by step by the algorithm. Because of the least squares aspect of the algorithm, simple sets for f of z do not have to be determined carefully. It is usually enough to distribute a few hundred sample points with reasonable density along the boundary of the domain. The contours in this and the other plots are potential curves associated with the poles and interpolation points, as we'll explain at the end. Next, suppose f is analytic on k but meromorphic in complex field minus k having 1 or more poles. Here rational approximation can peel the poles off, so the decay of error sub n is still super exponential. Polynomials, however, are limited to exponential convergence at a rate determined by the pole closest to k as measured by a conformal map of the complement of k to the exterior of the unit disk. Figure 2 illustrates all this for f of z equals tangent of z squared on the unit disk, with the rational curve again curving downward, but the polynomial curve now straight. 4 poles are off scale, and similarly there are 4, 1, 4, and 5 poles off scale in figures 3, 4, 5, and 6. Let's look at figure 2. The caption says, meromorphic function f of z equals tangent of z squared. On the left side, we see that the polynomial approximation suffers diminishing returns as we increase n, whereas the fraction of polynomials, that basically gets better and better, although, interestingly, not perfectly monotonically so. Anyway, on the right side, we see the function that is trying to be approximated. We see the various different poles in red, and the points being interpolated are in yellow. Is that what yellow was? Yeah. I wonder why all the interpolation points are in a circle. Anyway. Now suppose f has essential singularities outside k. You might expect this to slow down rational approximations fundamentally, but in fact the convergence is still super exponential, as shown in figure 3 for f of z equals exponential of tan of z squared on the unit disk. The contour plot looks much as in figure 2, but each of the inner 4 red dots is now a cluster of 5 poles as illustrated in the inset. Figure 3. Function with essential singularities, f of z equals exponential of tan of z squared. And on the right side, they zoom in a little subfigure on near z equals radical pi over 2 to show that actually there are singularities clumped together. And again, the polynomial approximations suffer diminishing returns, while the rational approximations, very surprisingly, continue to get better and better as n goes up. Well, not strictly monotonically, but almost monotonically. Branch points are a more serious obstacle to approximation because they are not isolated singularities. If f has any branch points outside k, rational approximates always slow down to exponential convergence. Thus, both rational functions and polynomials converge exponentially, but the rates may be very different. I like to think that the trouble with polynomials is that their poles are constrained to lie at infinity, whereas rational functions can put poles wherever they are most useful. The poles of good rational approximations do their best to approximate branch cuts, lining up beautifully along certain curves investigated by Stahl, as one sees in figure 4 for approximation on the unit disk of a function with square root singularities as z equals 1.5 and 1.5i. Figure 4. Function with branch points, f of z equals radical 1.5 minus z quantity of 1.5i minus z. Finally, there are two great cases where rational functions are far more efficient than polynomials. The well-known one, as discovered by Newman in 1964, is when f has branch point singularities at the boundary, on the boundary of k. Here, polynomials are stuck with algebraic convergence, whereas rational functions can achieve root exponential convergence, that is to say, big O of c to the minus radical n, by clustering poles exponentially near the singularities. Figure 5 shows Newman's example of approximation of f of z equals abs z on the closed interval from minus 1 to 1. The rational approximations converge root exponentially, whereas the polynomials do no better than big O of 1 over n. The other case is not so well known, but equally important. Well, let's look at figure 5 first. Figure 5, the caption says, function with singularity on the approximation domain f of z equals abs z on the closed interval from minus 1 to 1. The other case is not so well known, but equally important. This is the situation of approximation on a non-convex domain when the analytic continuation of f has a singularity in an inlet, as will be true in most applications. Here, both polynomials and rational functions achieve exponential convergence, infinity norm of f minus r equals big O of c to the minus n for some c bigger than 1. But for polynomials, c is exponentially close to 1 with respect to the length of the inlet. In the case shown in figure 6, involving a smooth domain k bent around a portion of the positive real axis, we would need to increase the degree of p asymptotically by about 500 for each additional digit of accuracy. In such cases, for practical purposes, polynomials effectively do not converge at all. The rational functions do fine by approximating a branch cut along the closed interval from 0 to infinity. Figure 6. The caption says, function analytic in a non-convex domain, f of z equals radical minus z. The shaded gray area is the region where it is analytic, I suppose. I mean, it would be analytic outside of that area, but you have to draw the line somewhere. They wanted it to be open, I suppose, or whatever. And then lots of poles. Kind of looks like Pac-Man. Now, at last, let us explain the contours in the figures which show off the Walsh-Gonchar theory that leads to all of the results we've outlined. These contours are level curves of a potential function phi, which we can interpret as generated by a positive point charge at each pole pi k and a negative point charge at each interpolation point zk. Phi of z equals product k equals 0 to n z minus zk over product k equals 1 to n z minus pi k. This yields an error estimate for r by a Cauchy-Aramy contour integral exploited by Joseph Walsh beginning in the 1930s. F of z minus r of z equals 1 over 2 pi I, integral over big gamma, phi of z over phi of t, f of t over t minus z dt. This identity holds for any contour big gamma within which f and r are analytic, and good bounds come when the pole and interpolation point distributions are close to equilibrium. Behavior as n goes to infinity was investigated by Gonchar and others beginning in the 1960s, and the best bounds come with big gamma lying as far from k as possible, hugging Stahl's optimal branch cuts. The AAA algorithm doesn't know the Walsh-Gonchar theory, but its poles delineate the optimal branch cuts pretty well anyway. Something remarkable emerges if one examines the numbers on the color bars in our plots. These represent powers of 10, and what's striking is that the range of yellow to blue is typically around 7 orders of magnitude, not 12 or more, as equation 2 would suggest for 12-digit accuracy. What was equation 2? Equation 2 was the integral equation for f of z minus r of z. There is a factor of 2 in play here that is related to a certain orthogonality or approximate orthogonality along contours. Simply put, taking absolute values in the integral equation for f of z minus r of z gives a valid upper bound, but the actual error is often much smaller because of oscillation of the integrand, leading to cancellation of the integral to leading order. For many near-best approximations, error sub nn is on the order of the square of what one would expect from the equation. Rachmanov speaks of the Gonchar-Stahl rho squared theorem, which details cases in which this squaring can be guaranteed. The easy computations and plots of this review would not have been possible before about 2018. The implications of the AAA algorithm are very wide-ranging, making rational functions practical for numerical computation in a way they never were before. Exploring the possibilities is an active research area in numerical analysis. Too bad that the paper didn't actually detail what the algorithm actually does, but I suppose that would be far beyond the scope of a 4-page paper. Interesting, and lots of pretty pictures. I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. See you in the next video.